happens if I add a little red bump here to the curve? And when you do that, how are the flow line going to change? So this is one of the most natural problems in analysis. Riemann introduces Riemann mapping. The question is a Riemann mapping continuous in the boundary of the domain, which could be a parameterized curve in this case? Is it differentiable in that boundary? And in fact, what kind of functional is it, right? It maps a curve to some change of variable from arc lengths to some point to function to values on the line. And in what way is this is actually nice? So it turns out that it's really not, well, it is quite difficult, but the result was quite surprising. So the first question is, how do I measure the distance between the curve with a bump and the curve without the bump? And in fact, what is the size of that difference? So the way it came out is this: we looked at the operator here, which is a Cauchy operator, and we said to every curve there is such an operator, view it as an operator from the curve into itself. Let's pretend for a moment it's bounded on L2 of the curve relative to arc lengths. Then I can compare two curves by comparing the size of the operator attached to it. And as it turned out at the time when Meyer and I discovered that in fact the distance between the operators is essentially some distance between the argument of the curves when they're parameterized by arc lengths, in other words, the argument of the usual thing. And the norm, so this distance is equivalent to what is called the norm of bounded mean oscillation, which basically measures the maximum local L2 variance of this function. So this norm was around, introduced by John and Nirenberg years ago for PDE, but it pops out this way. So basically looking at this analytic question gives us a geometric insight about how to measure the distance between the curves, and was quite nice. It turns out that once you know that, it is a very easy translation from the Cauchy transform to what is called the second transform, which is contained by the Riemann mapping. So you get the Riemann mapping, you get that the Riemann mapping, in fact, is analytic on the manifold of curves if the manifold of curves is parameterized in this Banach space manifold structure, which is the BMO of the argument. And the space is defined as being, in effect, the largest space for which the Riemann mapping is differentiable or analytic for that matter. So that's... this was quite nice, but I'm going to relate it to how you do data analysis and understand, try to figure out how the brain of a mouse works. Okay, so it really goes way out. So, by the way, those results were later extents of this characterization of the kind of curves we were dealing with. By the way, the conditional VMO for small, basically is equivalent for small values, for small norms, to say that the curve are verified the Kodak condition, which means that the ratio of the lengths of the curve between 2 points and the lengths of the arc between those 2 points, and the chord between the 2 chords is bounded. So it's completely geometric. There's nothing, no analysis, no nothing. It's just the curve doesn't pinch itself too much, and it's done under control. Those kind of results were extended later by Peter Jones and Guy David and Stephen Sams to basically subsets, codimension 1 subsets in Rn, and then more generally, in fact, this kind of condition gives rise to a very detailed and deep theory on how to organize sets. In particular, if you want to answer the question, do I have a set of points, can I parameterize it by, say, a bi-Lipschitz map in 3 variables, for example. And so there are direct numerical conditions to do that, which are local estimates that you do. This also relates to the so-called traveling salesman problem, the way Peter Jones was doing it. You have a collection of points, you want to estimate the length of the shortest curve through them without computing that curve, but just doing local estimates on variability from straight lines. In any case, I'm getting to my story, which is what we have here. You see this, so this is, now I'm sort of jumping several steps ahead, and we'll flip back and forth between them. So you see this molecule that is pointed out to here, the arrow points to it. It's an alanine dipeptide molecule. It has 10 atoms, and what we were doing is basically simulating, knowing the energy of the molecule at any given configuration. You can basically stochastically simulate the molecule in water. So when it's in water, it sort of vibrates and oscillates a lot. And so what you collect really is a collection of configurations in this dimension 30 basically, because you have 10 atoms, 3 coordinates per each. Of course you should reduce the dimension substantially, but what you see, you don't expect the thing to be very complicated. The molecule, the atoms could be anywhere, but they're sort of basic places where it would be, because the shape of the molecule is governed by those 2 axes that you see that are pointed to. You see there are 2 angle variables, which basically tells you how it's shaped. And then, of course, it vibrates a lot from that. Once those angles are frozen, you may find many configurations like this. So think of it, there is a state of the molecule which is sitting in space with the 2 angles at a certain configuration. But our goal was not that. Our goal was, can we find those angles just from observations? And do we need to observe the full molecule to do it? So the point was, don't do that. Just let's try and do the following. Can we, say, observe only 5 of the atoms, and then from that get the coordinates, which are the position of the 2 angles in space, from the 5, and then take another set of 5 atoms, and can I get the same angles? And in fact, can I get a representation which is going to have to be nice enough to be sort of independent of the observation mode? Okay, so it's like, mathematicians have been always saying, well, I have a manifold, say, surface in R3, I can write local coordinates for the surface, but that depends on how I do it, right? Every time I turn the surface around, I get a different set of coordinates if I want to do it by, say, projecting on some planes. But the issue is there sort of an intrinsic way of assigning coordinates? And as you will see, not only there is one, but we should use it for years when dealing with Riemannian manifolds. And so here, the underlying assumption here, basically, this is mostly a 2-dimensional manifold, basically given by the angles, those 2 angles in there, and we want to let's cover that manifold with its internal intrinsic metric as it comes. And so what you see is we've observed the molecule with 5 atoms on the left. We've observed it with 5 atoms on the right. We found two basically what we call intrinsic coordinates, which is the x-axis and the y-axis, which are basically the eigenvectors of a diffusion operator, or a probabilistic kernel, which I will explain in a few minutes. And you see the molecule with this observation of the other. The color, by the way, represents the size of, say, one of the two angles. And as you can see, the color on both representations, it's pretty good. We actually measure the relevant variable quite nicely from this set of observations. So it's remarkable. In other words, there is some sort of innate truth floating in there, and we want to pull it out. We don't care what instrument we're using. We would like sort of a characterization of some latent variable or parameters which describe intrinsically the changes of states of that molecule. What is really happening in this case is that we don't match a point to a point. What we do is we observe the molecule for a little while, so we observe a little cloud of basically a neighborhood of a given position, because this is stochastic in water, and then we're comparing the statistics of that neighborhood to the statistics of a neighborhood of another point, and that's how we relate points to each other. Comparing statistics has the advantage that you're not pre-specifying how you're going to relate things to each other. If probability is probability is probability. If you can measure it, you have automatically an intrinsic way of seeing the world. So let me go back a little bit. So this is about 11 years ago. We were working on this, trying to use the sort of diffusion processes to organize data. And Amit Singer, who was working with me and who's going to give a talk this afternoon, made the observation that if you want to solve an old problem, we were looking at a sort of problem related to cryo-EM. He probably will talk about it quite a bit more. And if you wanted to solve the problems posed already by Cauchy, so you see we're going back in antiquity, which was how do you determine the shape of a body, a rigid body, if you know for every point in it, say, so it's a discrete Tinker toy, if you wish. It's a discrete body, and for every point, you know the distances of that point to a few of its neighbors, and the underlying assumption, which is not obvious but can be checked, is that you have enough information to define to have the point rigidly defined. Or for example, you think of it this way: you have the cities in the U.S., and you know for each city a few other cities in the neighborhood, and you know the exact distances between them. Can you assemble the map of the U.S.? I mean, so how would we do that? I mean, it's very simple. I mean, you take a point, and you look at, say, there's 3 or 4 or 5 neighbors. So if you have enough neighbors to do basically trigonometry to determine all the angles, then you can easily write every city, as is here, as a convex combination of a few of its neighbors. Okay, and so that would be your model. And once you've done that, you can. Okay, so that's a local linear model, if you wish, of how the cities relate to each other. So for every city, you compare it to a few neighbors, and you describe the city as a convex combination of its neighbors. So suppose you've done that, then the solution of the problem is staring at you. It's right sitting there, and that was a genius of Amit Singer. He saw the obvious, which, by the way, escaped a lot of people. People have been at the time actually looking at this thing, and using supercomputers to compute the map and so on. Okay, and you can do it in a minute on your laptop, in a second on your laptop. So if you read the equation, it says that basically the points have to be essentially fixed points of this matrix applied to them. Or if you wish, the x-coordinates of a point has to be an eigenvector of this matrix. The y-coordinate of this point has to be an eigenvector of that matrix. And the vector whose constant entries are 1 is also an eigenvector of this matrix viewed on the space Rn, where n is the total number of points that you have. Right? So for every point you have a few neighbors, you have a million points you have. You can take 5 neighbors per point, that would be good. And so the eigenvectors automatically give you, and so now you want to get the actual map. It's obvious, right? You compute the first 3 eigenvectors of this matrix, corresponding to eigenvalue 1, assume that's all there is, which is sort of implies some rigidity. And then from that, you just have to basically write. So x is a linear combination of the 2 eigenvectors you found. Y is a linear combination of the 2 eigenvectors that you found. If you set 0 to be the center of all the points, so the average of the points that you have is 0, then 1 is orthogonal to that. So you need those 2 eigenvectors. They're orthogonal to 1. And now all you have to do is find 2 parameters, but then take 3 points that you normalize, a triangle that you normalize, and everything is scaled to that. So you're finished. The whole problem is solved, obviously. Now, it shows several things, and the reason it shows that example is the following. How would I actually solve this problem of, if I know the local model of the data, which is I know the local configuration, I can actually by trigonometry figure out what the local map is, how do I actually get the global map? Okay, the way you do it is by integration. So in other words, you take a piece of that puzzle, and you look at the neighboring pieces, and you match them, and keep on building the puzzle until you got the whole map. Okay, when you do that, starting at a point, and you do it, you risk actually making mistakes along the way, and finding Denver and San Francisco close to each other. Okay, so the point is, but it's a process of integration. In fact, this allows you very simply, this extends the fundamental theorem of calculus. If I know the difference of the values of 2 functions at 2 neighboring points, and I know even the absolute value of the distance between 2 neighbors neighbors and maybe one neighbor beyond, it's easy to reconstruct the function through this eigenvector, which is solving the fundamental theorem of calculus, right? And you can solve many other equations that way. But there's another point in there. How do you actually find the eigenvectors of a matrix? You start with a random vector, you apply the matrix, you normalize, apply the matrix, normalize, apply the matrix, normalize. If the random vector were a point, and you sort of propagate your knowledge from that point further out and further out and further out, you're integrating. But you could start points scattered randomly around and do this integration process from all directions at once. So it's actually more robust. And finding the eigenvectors is also more stable than doing the sort of local incremental informational assessment, if you wish. So the general process of sort of linking and understanding coordinates on sets of points. So again, let's come back to my example that I had before. The example of this molecule, so I had, say, millions of sort of different states of the molecule that I have generated by machine or I measured, whichever it is, and I want to find out the manifold of those two angles in there. So how would I do that? The way to do it is to get the invariant coordinates. Since I want it to be also independent of the modality of measurements, I want the invariant coordinates. So the simplest way is to, again, try to estimate the probability that 2 points x and y are in the same state. So you can measure that probability very simply by, say, looking at the cloud of points around x, the cloud of points around y, doing some statistics on the two clouds. In other words, I can build some histograms around x and histograms around y, and now I need to have some metric which measures their distances, and I'll return to that a little bit later, how to match cloud of points. And you can define a kernel, which is basically pxy, essentially representing the sort of conditional probability or conditional correlations between the cloud at x and the cloud at y, or the state of x and the state of y. This is one thing here which is open to discussion, and if you want we can do it offline. So this kernel, because it is probability, it really, so what does it do for you? It basically represents essentially the constraints. If you think of the kernel as some sort of correlation or covariance between x and y in some high-dimensional space, it sort of represents a local model relating the points to each other. Okay, so it's like what we did with a tensor, with a tensor localization system, where we had a local model. It represents that sort of local model. So once you've done that, you have this kernel pxy. So again, you can think of x and y as massive discrete matrix. So in the case of a million samples of this vibrational molecule, I could take a million by million matrix. There's no need to do that, but you could. And then take that matrix and just diagonalize it. Okay. The eigenvectors of that matrix, okay, are basically functions of x. Okay. Being functions of x, they are variables that I can use to describe the position of x. So this is sort of the eigenvector embedding of my data into some high-dimensional space. I can decide I want only to look at 50 or 100 eigenvectors if that's sufficient for my needs. By the way, the number of eigenvectors you need is at least as big as the number of constituents or clusters, if you wish, in the data, or different states of the data. If this molecule here, if I run my experiment and I find that there are maybe 100,000 different states that I can match to each other, that's how many eigenvectors I would need. There's nothing I can do about it. Nature is what it is. So this embedding is really an embedding which should be viewed as an embedding in Hilbert space, just like the embedding of Riemannian manifold by associating to a point a diffusion, a heat kernel. And here I'm associating not to a point a heat kernel, but to 2 points. The probability that they're in the same states, in the case of a Riemannian manifold, whatever this probability is going to be some function of the geodesic distance between the points, because if I'm basing it on heat. So the eigenvectors of that are not automatically going to be eigenvectors of the Laplace-Beltrami operator of the manifold. And so it basically tells us something, and I will return to the Laplace-Beltrami in a minute, but it tells us I can use the eigenvectors of any manifold, the sort of intrinsic coordinates, to use if I wanted to build atlases, if I wanted to analyze data, whatever it is. And the point I want to make is that you don't want to restrict, the manifold could be dimension 2, like it was in the molecule, but it could also be dimension d, and you still may need to have a very, very large number of eigenvectors to get good coordinates. Think of the manifold as like a collection of grapes to each other. Every grape has its own coordinates, right? You can't do anything about it. So here, coming back to the manifold, there is a theorem proved by Peter Jones, Mauro Maggioni, and Anand Shul not long ago, after we started this adventure, that in fact, if you take a Riemannian manifold and you want to construct a coordinate system around the point, then you can always find eigenvectors of the Laplace-Beltrami operator that give you, sort of in some ways, an optimal description of the coordinates around the point. And so they take a patch which is maximal. You can choose them so that they will map the maximal patch into a d-dimensional Euclidean space. And depending on the point, you will take a different set of eigenvectors. So they're sort of a universal library of functions that you can use to build any atlas you want of the manifold. And of course, because they are eigenvectors of something which is intrinsic, I mean, they don't care about where you saw the manifold. The manifold could have been some sort of very embedding high dimension, low dimension, it doesn't really matter as long as the notion of neighborhood in whatever version you have is the same. So you need for every point to know who the neighbors are at the point who are at distance epsilon from the point. I mean, Riemannian distance epsilon from the point. If you have that, you have the metric. You also have an operator which is averaging on that cloud of points. And the eigenvectors of that are the eigenvectors of that. They don't care. You have intrinsically defined everything. And you got this collection of functions. So here, let me show you how you apply that. Okay. So this is a process which is about maybe 5 or 10 lines of MATLAB, okay, without knowing anything about anything. So what it does is this: you have this image here, and I pick a pixel. I don't know if you, okay, you see my pointer on the scarf here. And but that pixel, okay, that's my point of interest. Now I want to organize a manifold on that picture. What would the manifold be? I can take for every pixel, I can take the 5 by 5 patch around the pixel. That's a vector in 25 dimensions. I mean, the gray level, which coordinate is a gray level of the corresponding 25 pixels. And now I decide that, so in this case, I just pretend that the right probability that pixel P is going to be of the same kind as pixel Q is just e to the minus the distance between the two patches scaled appropriately. So when I do that, what happens is that I can now, so I have an operator, which means, what is the operator? I take a point. I take a function on this image of which a function is a function of P. And then I average it on all pixels which are neighbors of P. So this is like averaging on the neighborhood of the pixel P. The eigenvectors of that, I collect the first 50 of them. But then I do something much more interesting. I could go back to what I have here, which is I would like to find which eigenvectors for a given pixels give me a good description of the neighborhood of that pixel. Okay? So returning here, that's exactly what I did. So I found that the eigenvector 5, 8, and 10 are the ones which are the most active at that particular location, which I indicated here. And those eigenvectors, well, there's 3 functions, so there's 3 images. Because there's 3 images, I could represent them in red, green, and blue. And then I have this image underneath. And the neighbors of this pixel here is everything that you see here. Mostly the eigenvectors that really counts is the green one. And you can see them here. So all I've done is translated this geometry that we have here, right, to the geometry that we have here. And that's nothing. That's beautiful processing. And if you wish, it's a processing in which I connect the dots, right? I'm doing the same integration I described before for the sensor localization, which is I'm saying I'm going to connect each pixel to the neighboring pixels because the patches around them are more or less the same, and I'm going to track those sub-images. In the picture, tracking those sub-images, I will find a region corresponding to that particular location which will have interest. I will show you later that we are going to do things like this to track the activity in the brain of a mouse, and it's much more interesting. So the question, there is a question which is fundamental in all of that, which is what is a good way of matching 2 subsets of points in Rn. So for example, I could have those 2 curves, and I want to measure a distance between them. So we have heard here, and we will hear again and again and again, that a good way of measuring the distance between 2 probability distributions, or which says I can use each one of those curves as being a density and normalize it to have density 1. And then how do I measure the distance between those 2 densities? There's something called transportation distance, or Earth mover distance, which says I'm going to take points on one curve, trying to find a map to the other curve, and then pay the price of how much I move the point around, and then try to, among all possible maps, minimize the total amount of work I have to do to go from one curve to the next. So that's very nice, but not necessarily very easy to compute. There's a much simpler way, which is to do this. You just take the curve, make it fat, now they look much closer to each other, and make it fatter, now they look identical. At every scale, I want to measure the distance between the fattened curve with a weight which goes up with the scale. So in other words, when the scale is large, everything is the same. I have to sort of compensate for that by multiplying by a large number. And when it's low, I don't want to use that. Here the distance is 2. Right. Basically, they're missing it now. So the issue is that one needs to have to do that. When you do that, so by the way, this Earth mover distance can be computed if the penalty that you're taking is Euclidean distance to some power less than 1, can easily be computed by just doing exactly what I did. Just average and compare. Compare different scales. This is equivalent to some Bessel norm on the distribution defined by the Points group as a dual of the function, which are Lipschitz or something, not Lipschitz Holder. And then you can use wavelets, or you can do those kind of ways. This is sort of relatively easy exercise, very fast to compute. But the point of that, it allows you to organize families of curves. So when do you get families of curves? You get them, for example, when you have a dynamical system. So here, this is the standard map on the torus, which is defined by those equations. Up there, it has a lot of orbits. The orbit space is described as this color image. And the issue is, what is the structure of the orbit space? So for the topologist among you, it's clearly nice. You would like to understand that. Not only that, but there is a parameter alpha floating in there. And you want to organize not just a single orbit, but the family of all dynamical system as a family depending on parameter alpha. So every dynamical system is basically described by this collection. For each alpha, you have this image on the right, but then as alpha moves from, say, 0 to 1, you have a whole movie. And you want to understand the structure of all of that, right? And so you can do by, again, building a joint graph. I'll come back to that. We'll do a slightly more interesting thing. Okay, so another aspect of this geometry of points in Rn is that when n is small, it's not so interesting for an analyst. Okay, when n is large, it becomes much more interesting. And you can think of it as looking at the following situation. You have some, let's say I have a large collection of points, let's say the cloud of stars in the universe, or just inside the galaxy, and there's gravitational interaction between them. And so basically, for every pair of points, you have the gravitational potential which relates the relationship in this universe, right? So the data that one has here is basically a very large matrix, which is a matrix of all stars that you have measured, and basically the matrix of one of the distance between any pair, right? So for every star, you have the interaction of that star with all the others. So every point, if it interacts, assumes that it interacts with another 1,000 points, and everything else is sort of negligible. You have for every point, you have 1,000 points. With which it interacts this matrix, but still, a million points, you have a million matrix. So your data is a million points. Each one interacts with another set of million points. And what you want to do is organize them in a way where all the dependencies are sort of washed out. Okay. So this is done in numerical analysis. Of course, you cannot do anything with a million squared matrix, or at least you couldn't. And so there are methods like the fast multiple methods introduced by Rocklin, but even going further down, the Kaldor-Zygmunt decompositions introduced by Kaldor and Zygmunt, in which what you do is basically organize the points into a hierarchical collection of boxes, and so you organize the columns of this kernel and the rows of that kernel into two different organizations, depending if it's the same space, it's more or less the same organization, but it did not be. More complicated than that, you could try and do the statistics in this orchestra hall, or in this no hall. Okay, and it doesn't matter what you do unless you organize all the points where you want to. You say you want to have the best possible acoustic at every location, and you have all the reflections coming from everywhere. So you have all the people here are the sort of the receiver, and all the sources are the various points where the sound is reflected from. And so you want to relate one to the other and organize this universe. Okay, at this point, at least to my knowledge, no machine learning will do anything. Okay, it's way too complicated. Both in terms of how many measurements and how much variability there is in there, you really have to organize that to this universe. So that's what I'm going to describe how to do it. So the way we want to think about it is like a big monster questionnaire, okay, in which every person in this room is basically constantly assessing the quality of the sound, if you wish, and then there's a various location which is generated. Anyway, let's go back to this example I had before with the Cauchy transform, which I measured. So you have this curve, and let's say that PFS represents a point on the curve parameterized by arc length S. The function 1 over PFS minus Z is a function on the curve. So you have a curve, you have all the points on the curve, and you have this collection of functions on the curve. So when you have, say you have a questionnaire, and I'll show you in a few minutes maybe a psychological questionnaire of people, you have 500 questions. Every question is a function on the people, okay, and every person is a function on the questions. Right? The responses are a function are the. Now, what I want to do is show you that you can organize the geometry of the questions and the geometry of the people in that case in such a way that all the redundancies, or many of the redundancies and dependencies are sort of washed out, and you try to represent it in a much simpler way. Okay, that's one of the goals. The other goal is to actually process all possible information that I may be interested by in the future after I've organized the geometry of my data. So in the case of a database, which is a questionnaire, people being asked questions, and you have responses of thousands of people to hundreds of questions, and you want to organize of psychological responses, you want to do it so that you can actually use that to compute functions that you haven't asked about. Like, for example, how dysfunctional is that particular person, okay, or how effective it is, okay, or so on. So in the case of the Cauchy transform, the functions we were looking at are basically the functions, the holomorphic function on the curve, which have a pole, and the simple functions having a pole at Z, right? That was a Z of the curve. That's my collection of functions, and I organize the geometry based on that collection, okay? So I can organize the geometry of the Z's, which are the various locations. That gives me something like a Whitney decomposition of the upper half space, or the space next to the curve, and then the geometry of S, which is the usual geometry of the line that one has. So I think I'm running out of time, but basically the process is, I'm going to skip a lot. So the process is you have sort of organized matrix, which is a ground truth, that has been permuted around, and you want to be able to recover it. Here I've done the same. I took this image, and I basically converted every pixel to plus 1, 0, between 0 and 1 by calling this probability, which is a gray level of image. I get what's up here, and I need to restore the original image. So that's sort of the generic problem. You can do quite well in doing it. A more interesting example is what I said. You have this 3,000 people, 500 questions, answering yes or no to the questions, and that looks like the garbage picture on the top left. And the issue is what you do with it. Okay, and the point is you can get it organized into groups of people which will have similar response, which is what I was describing before. Say 2 people likely to be in the same psychological state based on their answer. That would be my kernel, and I can use that to organize the people into groups. I can also organize the questions by 2 questions relating to the same, or basically asking the same thing, and by just saying the population, how similar the responses are. So I also have an organization of the rows of this matrix, and the joint organization is one where you want to have a simple possible structure. The simplest possible structure you see the highlighted box here, shows you that in that group of columns and that group of rows, basically the response is a barcode. Okay, everybody in the group gets the same answer from that group of questions, and everybody gets the same. So this geometry can be extracted from the thing by iteration. The main point here is that none of that works if you ignore the facts of life, which is that many questions are equivalent to each other. They're basically asking the same thing. People tend to get tired of answering questions. questions, and they sometimes put anything down. So if I compare the response of a person to the response of another person, I may have a lot of responses which are basically noisy, misfits, and it's not very accurate. I should do much better. I should compare the response conceptual group of questions to the response for another person to a conceptual group of questions. And that will basically give rise to an Earth mover distance between people profile. Similarly, once I've organized the people, then I get a response of how I get the understanding of whether questions are related to each other. In other words, I see to those two questions the same groups, certain groups of people or all groups of people the same way, so they must be related. Okay, so the issue here is to eliminate the dependencies between them. So when you do that on the psychological questionnaire, you get a beautiful manifold describing the people, and the people who are the blue highlighted people here are completely functional, as verified by the graph on top is something that came from the psychology. Well, let's say the second one is depression level. I don't know what the others are, but 0 is the mean, and it's in standard units of standard deviation for various psychological conditions. So you see that everybody, and being outwards is bad. So everybody in the blue group is in trouble. And the other extremity, everybody is incredibly stable and functional and so on. And again, I'm really trying to, my message here is that this nice two-dimensional geography of people came about, it's not real. Okay, it's really something that one imposes on the data. If I were to actually organize the people by similarity of profiles, I'll just get something that looks like a Gaussian cloud. Okay, the reason they're so well organized is that I'm defining a similarity of people between people which is rather smooth, in the sense that I compare them by responses to large of questions. Suppose I split the question into bad questions and good questions, and then I basically classify a person by the proportion of bad questions he answered yes to. Okay, then I have a one-parameter curve. So this two-dimensional manifold will look like. And that's it. The way of setting it up, I'm basically doing signal processing on the data by imposing how to measure similarity between clouds. So again, my point is that it's very nice to let mathematics dictate, but it's also related to anything sometimes. Okay, you let mathematics dictate, but you have to understand how it imposes, how it changes the metric space that you're dealing with, what it discriminates among, and what kind of discrimination it provides, or similarity it provides. I'm at the end of my talk. Let me just skip this. Let me just say that this is interesting for the people do spectral theory. If you take a Riemannian manifold and basically take the eigenvectors of Laplacian on that manifold, and then you say, well, let's look at this as a questionnaire. Every eigenvector point has a certain value. I'm looking at the collection of eigenvectors as the responses to questions that the point is asking. So my situation is I have points, I have questions, eigenvectors are answers. How do I organize? What is the geometry of eigenvectors? Okay, I have a Riemannian geometry on the manifold. How do I the corresponding dual geometry on that? And so if you deal with them like a psychological questionnaire, it works extremely well. So for example, take the function sin kx, which are the eigenvectors of second derivative on 0, 1. You organize them, and then you see that an organization with a little bit of cheating, you can get an organization of both k and x's. The cheating is that you're assuming you have a little bit more x's. Eigenvectors are orthogonal, so you can't tell anything. But if you sample twice in x, you can organize the x variable, and that organizes everything else. So you need a lever to start with. Okay, the point, let me just, this is good. You see that? We wanted to understand the brain of a mouse. So this is a pendulum with a constant changing over time. Okay. And we took a video camera of that, and took an image of this pendulum, and then projected it into, I think we have 100 dimensions. We took 100 displayed as an image. And you can barely see it. It's sort of, can you run the, I don't know. When you run it, the different pixels fluctuate, completely random. So the question was, can we derive from that the actual normal modes? So at every time the spring is constant, so they're natural frequencies. And so that's again exactly what you get by doing the process I've described before. You actually get the physical normal mode by finding the intrinsic variable of that system. You see here the spring constant is changing all the time, and I'm going to finish with those pictures. So this was a model for what you get here. So here's a picture is this. You have who is basically going to go and grab some food and eat it, and you image the tonal fluctuation in the window in his motor cortex. So what you get is, this is just a snapshot on the left of raw data that you get. On the right, you get the underlying geometry of the neurons in there. It looks like a sort of vegetation patch under, and the corresponding cleaned activity. But here's where the challenge comes in. When he does the same thing again, time, you get a different dynamic picture. So the issue is, how does one compare sort of neuronal patterns or weather patterns of activity in a way that's informative relative to the state of mind of the mouse at this time? Disappointed, happy, excited, or just ready to go to sleep, right? And so, again, we do the same thing, but everything I said can be done in that, except that it's three-dimensional in the sense that we are running 100 experiments. Each experiment is one video on 100 frame, and there's, say, 100 different neuronal groups in there. And so you analyze each one of the axes. It's a three-dimensional questionnaire, right? You're asking every neuron what it did at a given time on a given experiment, and every experiment what the different neurons were doing through all times in that experiment, and so on. And so the point is that you can extract the underlying physical model empirically. I'm not saying it explains anything, but at least you have some sort of guarantee that you have a description that you may be able to trust to actually do the do the science behind it. Okay, so this is an introduction to science.
Thank you very much for this wonderful talk. As you know, it's not really very feasible in this room to have questions asked from the audience and then answered by the speaker to the whole public. But Professor Korfman is happy to answer questions to people who would come up during the intermission. So I would encourage you to do that. We have had an overview where it's clear that we get a glimpse of a lot more, and there is a lot that is really intriguing and very interesting here. So let's thank the speaker again, and that closes this session.
Second session of plenary speakers. It is my pleasure to introduce now the talk by Peter Kronheimer from Harvard and Tom Woodcock from MIT. Peter and Tom are specialists in a wide range of mathematical areas, including differential geometry, gauge theory, low-dimensional topology, and mathematical physics. They're co-authors of literally dozens of papers, and using Seiberg-Witten invariants, they settled long-standing conjectures, including the Tom conjecture and the property P conjecture for knots. In 2007, Peter and Tom won the Oswald Veblen Prize in Geometry of the American Mathematical Society for their contributions to both 3- and 4-dimensional topology through the development of deep analytical techniques and applications. Their book, Monopoles and Free Manifolds, won the 2011 Joseph New Prize of the American Mathematical Society. And the title of their talk today is Knots, Free Manifolds, and Instantons. So please welcome Peter Kronheimer and Tom Woodcock.
Well, it's a pleasure and honor to be here. We'd like to thank the organizing committee for the invitation and obviously the tremendous amount of work that they have invested in putting on this event. This talk has sort of 4 parts. Peter and I will switch on and off. Please don't applaud in between. Yeah, so let's begin. We're interested in the first part of the talk. I'm going to describe one of our theorems and try and give you a very concrete idea of what it means. So we're studying knots. A knot is an embedding of the circle in 3 space with no intersections. The trefoil, here's the figure 8 knot, and the basic problem in knot theory is to understand if I have 2 such embeddings, when can I bend and stretch, etc., one into the other or not. Sometimes links appear in the story, so embedding of several circles. An important character in knot theory is the unknot, just the standard embedding that lives in a plane of the circle. And of course, there are many knots. If you organize knots according to the number of crossings in a projection, by the time you get to 16 crossings, there are nearly 1.4 million distinct knot types. So many that this poor knot 16N36441, this is its only moment of fame. The trefoil and figure 8 have a much more pleasant fame. And because there's so many knots, there are tables of knots with knot invariants computed, so there are many interesting conjectures that come about and trying to see what kind of patterns appear. So the main question that we're going to focus on is how do you recognize when a picture represents an unknotted circle or not. So is this a picture of the unknot? A basic tool in that study is the complement of the knot. And in studying the complement, it's natural to study its fundamental group. That's the group of homotopy classes of paths. Here I've indicated one such path that lives in the complement of the knot, starting at some base point, running around the knot, and then going back to a base point. Here's a different element of the fundamental group. Both of those curves are examples of ordinal curves. They're curves that go around and loop around the knot once and then return back the way they came. Another important fact to keep in mind about the knot group is that it's abelianization independent of the knot. Abelianization is the group of integers, Z. And that leads to the first kind of recognition principle for when a given knot is unknotted. It comes from Dane's lemma, which was not quite proved in 1912 by Dane, and then finally given a rigorous proof in 1957 by Papageorgopoulos. And it tells us that a knot is the unknot if and only if its fundamental group is Z, if and only if its fundamental group is abelian. So for us, in trying to recognize knottedness, one way to test is one way to certify that a given knot is knotted is to show that the knot group is not abelian. So and we can recognize that by exhibiting a homomorphism from the knot group representation with a non-abelian image. It's a theorem of Thurston's that actually knot groups are residually finite. So in fact, we know that therefore that we could detect the non-abelianness by mapping our knot group into some orthogonal group, isometries of some Rn. That's an interesting question. Then can I, will the same n work for all knots? Or if it does, is there a smallest n?
Gracias.